Jason. Okay, so just to remind you guys, somebody already said this, we do have that quiz tomorrow. Chapter 1 review and 2.1. We'll also have a quiz on Thursday. 2.2, 2.3.
This week?
Welcome to summer. 2.2, 2.3. I think it's good. Yeah, so in 6 weeks, we do what we normally do in 16. So they're going to come fast and furious. You want more grades, though. I'm sure some of you guys realize that. I had a class where the only grade was the oral final exam. You put us each in our own little room, and one of my best friends next to me in the next room, she had a nervous breakdown during the test. And he says, let me go take care of that. You work on this problem, and I'll come back and check on you. And she's over there going, ah! And I'm like, oh, shit. She turned out she was okay eventually. But yeah, you want more grades is the lesson of that. You want no nervous breakdowns, and you want more grades. Okay. So with that said, to get ready for tomorrow's quiz, any questions from that review section? Don't feel bad that it's a review. If you have a question, trust me, at least 11 other people have a question too.
Is there any key problems that we need to focus on from our warm-up from yesterday?
Oh, every single one.
Okay.
Okay. You're so helpful, Jeff. Yes, I know. I know students always want to know exactly what's going to be. But any of it can be. But it's actually a good point you bring up. I mean, if you want to see what seems to be sort of important to me, then that's one place to look. And of course, you know, I think I skipped over a few problems in the review section. So obviously the ones I assigned seem to be important to me. Yes?
I had a question. It was kind of vague. It's on the 11 through 16 problems. It says use transformations to sketch the graph of the function.
Oh, yeah.
What's the transformations like?
Uh-oh. So real quick, do you guys remember if I wrote this? Can somebody tell me what the vertex of that parabola is? Well, that's, you're telling me how to get to it, which is what I was going to lead into, yeah. The vertex would be 2, negative 5, because x squared starts 0, 0. This would move it right to down 5. So that's the transformation, right to down 5. So then the vertex would just move down there.
Yeah, I get that part.
All right.
I mean, do you graph the original equation? Or
Yeah, so anytime I ask you, or the book asks you to use transformations, you graph what I call a base function.
Okay.
So for this problem, this would be the base function here, would be, and you dot the line, you dot it, because that's not the answer. And then you move it, and then you move every point over, boom, boom, and then you make that last one solid.
So you can just use arbitrary values as long as it's the same.
Yeah, yeah. So for certain things, I use key points like negative 1, 0, 1 for a parabola. That's the heart of it. And then each of those points move around or flip if it's a reflection, right? Let me see what kind of stuff they throw at you. Yeah, they give you one reflection, a couple of reflections. Most of them are just. They give you one. I don't know if you guys remember this. Do you remember? Oh, jeez. All right, so the graph of this should not be a big deal. What's the graph of this? How does that compare?
Change the amplitude.
Not amplitude. Amplitude would deal with outputs. Where's the 2? It's in with the inputs, so it changes the inputs. No, well, every x value has to be how big. Like, what do you plug in here to get a 1/2 out? Pi over what? Sine of what is 1/2? Pi over 6. What would you plug here to get a 1/2 out? pi over 12. Because what's the first thing you do to the inputs is you double them. So all the inputs have to be half as big. So it actually compresses it. Sine and cosines are neat because they look like springs. So you can actually think about it like physically compressing a spring or stretching a spring. Is this slowly coming back? When it's in with the x, it changes the domain somehow. Right? That's why this is left and right. This is up and down because you can put it with the y. If it's in with the x, it changes the left and right somehow, which only makes sense because it's attacking the x variable, which is left and right. Is that decent? So you can have compression, elongation, stretching. You can have reflections. You can have translations, which is the easy one. Up and over and down and whatever. Oh, yes? Maybe so? Oh, shit. All right. I think... you should. Here we go. Section 1.3 talks about all of the transformations possible. Okay. Yes.
Could you use 16 or?
Oh, so 16 has its own interesting thing about the fact that it's a piecewise function, right? Piecewise functions always freak us out for some reason. What do they tell you? It's negative x, x less than 0, and then e to the x minus 1. Yeah, thank you. So I really never understood why piecewise was really that big of a deal. It's like you have to graph less of the graph. So you graph negative x, but you stop at 0. It's below 0. And whatever it would, so I always, you can make a little XY table if you wanted to, but that's not really the point here, right? The only place that's weird is 0. So the transformation here is a reflection. Now this problem I wouldn't give you a problem. This piecewise plus a base function with with transformations. To be honest, that's a little too much going on at once. So I don't necessarily, you don't have to do, here's x, it'd be back here, here's x, and here's the reflection. It's just really on this one, I'd rather you just be able to graph the damn piecewise function itself, right? So where is the open circle going to be? There's going to be an open circle here, possibly. Where might it be? 0. Because that's where now, does this guy fill this guy in? At 0, where does he want to be? 0. Can he be at 0? Can this guy be at 0? No, because it's not allowed to use 0. He wants to be here. Aw. Right? And of course, it's going to go, wah! There's negative x, basically, right? Now, please, dear God, understand this. I'm getting the idea. This shit is shit. If you turn this in, this is shit. By definition, this shit is shit. You give scale, give me some stuff, right? My God. Don't just give me this as an answer and go, I'm done. So when I teach pre-calculus, I actually say this to my students because they need to understand this. Pre-calculus is graphing hell. You've been through it, you agree. Because that's what it is. Why is it that way? So that when you get to calculus, you can do graphs easy, quick, and then you can focus on the calculus. That's one of the points of pre-calculus. This guy doesn't fill that circle in. Well, at 0, where does this guy end up? When you plug a 0 and you get... What's e to the 0? 1. Minus 1? 0. So it does fill it in. So it does end up being continuous. Right? That could have been a location of a different... Well, we'll talk more about continuous today. But continuous just means it doesn't come apart from itself. This guy filled this other guy in. It keeps going, right? And now, what's the general look of an exponential? I mean, you can plug some points in if you want to, but what's the general look? Can you guys put in the air the general look of an exponential? Yes. So from your perspective, it's this. Right? Is that cool? So, I mean, if you put a 1 in, it's going to be e minus 1, which is roughly Okay. Do you remember what E is? Something like, okay. All right, I'll leave that. You guys can figure out what E is for yourself. If you subtract 1. So it's going to look something like this coming off of there. Right, so it's really just taking, what would the transformation be here? It would be the e to the x, it starts here at 1, and shifting the whole thing down 1, which is why it goes through 0. I like it. Okay, so really piecewise functions are not difficult. They're cutting your work for a certain function in half, and then you just start there with the other function, right? And how do you figure out where to put the open circle? Well, you plug the value in you're not supposed to be able to use. Because you're going to put an open circle there saying, oh, I wasn't able to do this. Right? But this is where it wants to go. That's kind of like that idea of limit. Where does it look like it wants to go? Open circle there because I can't get there. Okay, cool. Anything else from the review stuff? Or the section 2 one, if you guys got into that, yeah.
For section 2, I did it on the website, so I don't know the actual number. But it's s equals 5 sine parentheses pi t plus 5 cosine parentheses pi t.
Oh, all right, let me see. So do it again, sorry.
S equals 5 sine parentheses pi t plus, close parentheses, sorry, 5 cosine parentheses pi t.
Okay.
And from there, the values were 1 to 2, and then 1 to 1.1, sorry. 1.
Oh, so it was, all right, I think there's a similar one. It's gotta be this one. There it is. All right, here we go. Yeah, all right, so here they just changed the coefficients. Find the average velocity, is that?
Yes.
Sounds familiar? Okay. During each time period. Okay. So, for example, if it said from find average velocity on t 1 to 2. So from 1 second to 2 seconds, find the average velocity. And of course, velocity is fundamentally just distance divided by time, right? The S function, they tell you, S is the letter that they always use for position. Yeah, displacement they call it, but yeah. Okay. So this, if I plug this in, it'll tell me how far I've gone. So it's the same old idea. What's this going to be? It's going to be the slope of the secant line through the points related to the inputs 1 and 2. So to find the velocity, it's going to be the change in position. So I want the position at 2 minus the position at 1. That's going to be how much the position changed. Is this cool? Yeah. What's slope? Change in the outputs divided by change in the inputs, right? That's really all we're doing is finding slope divided by 2 minus 1. And then they ask you to do, then they step it to, in the book they step it to 1, 1.1. It sounds like it was the same.
Right.
So this is part A. Part B says 1, 1.1. So what does it seem like they're interested in? They want to know the instantaneous velocity at what time? I can already guess where they're going. At 1, because I'm getting closer and closer to 1. So I want to know it at 1, and I start with my other point as 2. Here's 1, and then now my other point has gotten a lot closer. And then the next thing is going to let it get closer. The next thing would be 1, 1.01. Shocking. And then 1, 1.001. We're getting really freaking close. We're doing several steps in so I can see what the pattern is. I like it. Where are you at? Okay. Is that cool? Is that all right? So you just keep doing the same thing. So now I would do s of 1.1 minus s of 1 divided by 1.1 minus 1.
I think I was just caught up in with the other problems being like you're plugging in that time value that has an x value back into the equation to find a y value, and then going back and forth.
Yes, cool. Yeah, it's interesting. Every problem they give you is a little bit different. They all attack the same idea, but they do it in a different way. So it gets a little bit like, okay, which way am I looking at it this time? Yeah.
Thank you.
Sure. Anything else from review or anything in chapter 2? Did the review go okay? It sounds like at least some of you guys tried it out. I'm surprised no one's asking about like number, where was it? 23. I think I signed that one. That one's interesting. Okay, but that's up to you. You guys can ask about whatever you want to. And if you're like, I don't want to ask about shit, okay. No other questions from the review?
Number
Yes.
23 and
Oh,
number
23? All right. 23 is interesting because, well, for a few different reasons. You got to first get over what the real question is. So if you just plug 2 in, that ain't good. Because it ain't asking you for what's f of 2. It's asking you for what's f inverse of 2. How does that relate to the first line there? How does that relate?
You can find the inverse function.
You don't have to, thank God. But can you write... All right, now let me ask you this. Okay, f inverse of 2 is something I don't know. But it's going to be x. One thing we know for sure about inverse functions is the input for one is the output for the other one. So it's going to be some x value. Okay? This is one way to look at this. I don't have information about f inverse, and I don't want to find the inverse, because that would be very difficult, right? In fact, I don't know, this thing probably, I don't know this guy has an inverse. It has to, it's asked me for f inverse. But it's not going to be easy to find that inverse function. I don't know if you guys understand why. I mean, there's no real way to get x by itself easily at all, right? But what can I do to both sides of this so it relates more directly to that? What can I do to both sides? What do I know? I don't know x, I know f of x. So then what can I do to both sides? I love you guys so much. If I had x cubed equals 27, how do I find the real answer to that? What do I do to both sides? Take a cube root. Why the hell would you do that? Because that is the inverse of cubing. So what am I going to do to both sides?
Inverse both sides.
Inverse of the inverse, which is f. I'm going to f both sides. And you're like, yeah, that's right. F both sides. That's what I was thinking. Because what happens on this side? These cancel, that's what they do. That's the definition of them. They kill each other. So I get 2 equals f of x, which is 2x plus ln x. And then you're like at the same place you were with the inverse. You're like, I can't solve that, Jeff. The funny thing with this problem is you solve it on sight. I'm not going to tell you what the answer is, but you just have to kind of guess at the answer here. And it's not that horribly difficult. So don't make too much of this. If that wasn't there, what would the answer be? And what is the natural log of 1? Okay, that's all I'm going to say. That's all I'm going to say. Think about what just happened. But what's important is the real part of that problem is interpreting what they're asking you in terms of what they told you. You're like, the first reaction is, how am I supposed to do that shit? I can't find f inverse. You didn't tell me what it was. What the shit am I putting 2 into? You're not. You're not. You've got to interpret what they ask you in terms of what they tell you. You've got to do this kind of thing. There's a few different ways to think about what I just did. F inverse of 2 means what input has an output of 2. So I could have just said 2x plus ln x equals 2 from the beginning. Because this is the output of f is 2. That's what this says. Right? Because the inverse changes the input and output. So I could have just put this down from the beginning. I want the output of this to be 2. And then the answer is really so easy. You don't, thank God, because there's no way to really do that directly. You have to do it graphically if you want to do it some way. Okay, all right. So yes, I agree. That was definitely a weird one, but it's really testing. Do you really understand what inverses are and how they work in a general way? Do you see why I was concerned? So there are certain problems. If I don't get questions on them, I'm like, I doubt everybody could do this one. This probably means nobody did it. Check. In this case, it sounds like some of you guys looked at it and went, I don't know. So get over the feeling that only you have a question on something. This is not true. If you have a question from the review section, ask it. Not everybody's going to go, what the hell? What are you doing? Yeah.
20.
Oh, cool. I love it. All right. What does composition mean? It's not musical. Not. What is a composition of functions? What does that mean? No. Thankfully, because we haven't learned those yet. This is that funky ass notation that I hate. Right? It's like the students feel like they're in a... No? Okay. And the better way to write this is this. I don't understand this shit. It's bullshit. This makes a lot more sense. What's happening? G is being put into F. Right? So they want a composition of 3 functions. They want some function. This is the turducken of functions. They want some function in another function in another function. Right? DiCaprio's like, I don't want to make that movie. So let me do an easier example with just 2 real quick. If I add 1 over 1 plus 2 over x, and I want to know what's h of x, what are 2 functions that if you compose them like that, they create this? Can you tell me what seems that there's several different answers? There's one like kind of main answer. What looks to be like the inner function? What's the inner function? Yeah, okay. One way to look at it is 1 plus 2 over x. Let me give it. That's the first thing I heard. So if I say g of x is 1 plus 2 over x, what function did I put that into to make it do this? 1 over x. Another way to look at it is, what if the function, the inside function was... Notice how it's most important to figure out what the inside function is first sometimes. But notice I can look at the outside function. Doesn't that have the form of 1 over 1 plus something? And if that something is 2 over x. So in that case, the inside function would be this. And the outside would be that. As I slowly got. You guys get that? You can look at it either way. The whole thing is the inside. The whole bottom is the inside, and I put it into 1 over x. Or 2 over x is the function, and I put it into 1 over 1 plus x. Do you guys see that? Is that the only 2 answers? No. All the other answers are a play off of these 2, to be honest, but there's an infinite number of answers, to be honest. So, that's all I'm going to say on that. I want you guys to try. Now they want this bad boy. A function and a function and a function. But see how I could just step this out one more? Couldn't I right here say that g of x is 1 plus x? And h of x is 2 over x, which I put in here, which I put in here. Do you guys see what I just said? So you can actually start by pulling it apart in 2 and then pull one of them apart, and now you got 3. That's one way to kind of approach this. Okay, cool. This idea of a function inside of a function is huge in calculus. It leads to one of the rules that people make mistakes with a lot. I'm not sure how that makes you feel, but just to warn you ahead of time, I'll focus on how to not make the mistakes. Anything else from review stuff, chapter 2 stuff? Okay, I did devote a decent amount of time at the beginning for that, but if that's all we got. Last time we actually made it through 2.2. Let's kind of review a couple things. Is that going? Did I turn that on?
Yeah, it's still going.
Thank God. Sometimes I'll take a union break right at the beginning. So last time we started looking at the idea of a limit. And I kind of introduced the topics a little bit differently than the book, but they all kind of run into each other. So the idea of a limit is the first part of chapter 2. And one way to attack a limit is if I wanted to do a very famous one. One way to attack this is to create a table. So like if you don't know what a function looks like, you make a table of values. What would I create in my table? What would I do in my table to investigate this?
Plug in numbers.
Plug in
Numbers.
true.
Values close to
Put it
the
around
size of 0.
Yeah, close to 0. So like what? And I can try and attack it from both sides. So 0 is the thing I can't put in there. What happens when I put 0 in? Yeah, it becomes 0 over 0, right? That's an indeterminate form. I like it. So, which means, now, can I attack this algebraically? No, there's nothing to factor. I could try to use possibly some identities here, but that's not going to get me very far. Right, so there's real no algebraic way to attack this. There are some calculus ways to attack this. We'll learn later. That L'Hopital thing I talked about. So I want to kind of step in towards 0. So maybe I can do like 1, 0.5, 0.1, 0.01. And then on the other side, I could put negative 0.01, negative 0.1, negative 0.5, negative 1. Some people ask, why don't you just go straight to this? Because then you don't have a pattern to follow. You can't see what the path is without some more values. All right, so let's try this. Now, obviously, what do I have to be careful about when I go to plug stuff in? Well, 0 I'm not going to plug in. That's why I put it in parentheses. Is that cool? I'm like, I can't go here. But what I have to be careful about when I plug this in my calculator is my calculator should be in radian mode because there is an x that's free. It's not in a trig function. I showed you guys that thing with ask yesterday, if you remember that. But remember, it doesn't really give you good resolution. So you might not want to do that. Just make sure everybody's on the right track. What do you get for this? Anybody? Yeah, 0.814, blah, blah, blah. 841?
I got 8.4.
All right, I agree with you. What about, and I keep
It would
going.
be 5 since it rounds up.
Blah, blah, blah.
Yeah.
If I stopped, I agree with you, but I didn't. Sine of 0.5. What do you guys get? 0.95.
No?
I get 479.
For what?
Oh, I'm sorry. Divided by 0.5, thank you.
Yeah.
I forgot what it was. Yeah, so you get 0.95 something.
Yeah.
Blah, blah, blah. 0.1, so sine 0.1. Divided by 0.1, Jeff. There you go, buddy.
0.99.
Yeah, 0.99. So you can already kind of tell what's happening here. Do you see how it changed by a lot, and then it changed by not as much? And then if I go to 0.01,
It's like 0.99998.
oh crap, you do that. Yeah. 0.9, yeah. 99998. Just to be different. So definitely, now if you do the other side real quick, if you did sine, and now real quick, sine of 1 versus sine of negative 1, what would be the difference? Sine of radian of 1 versus sine of negative 1. How will it compare to this? It'll just be negative this, right? Then you divide it by negative 1. So it's the same as this. So all of these values are repeated here. You guys with me? You want to approach down. What does this relate to what we talked about yesterday? To investigate the limit at a point, I've got to look from both sides to make sure that they aren't doing this. Oh, shit. Right? So, but is everybody cool with what I just said? You don't have to put these in the calculator. We know how sine acts with equal angles, reference angles. Here it's positive, here it's negative. But I'm dividing by x, so the negatives cancel, all the same shit again. So it definitely looks like this looks like it's going to be 1. Right? That's my guess from my table. Has anybody ever done much physics? Any physics at all? Very often when you deal with pendulums and you talk about very small deviations from straight, if you pull it just a little bit, that your angle is very small, then sine theta is approximately theta. Look what this is saying. The limit of this ratio is 1, meaning for very small x, sine x is approximately x. That's what this is saying. You guys see that? If sine x over x is about 1, sine x is about x. So let's try it. What's sine of 0.04? Sine of 0.04. Yeah. 0.04 probably does some other stuff, right? Blah, blah. Aren't these approximately the same? Right? So that's really what we just showed. It's actually a huge deal. It makes it... I'd rather deal with theta than sine theta in a problem, to be honest. So it's nice to be able to approximate. But my deviation, if my how much it swings by is very small, I can use that approximation. All right, I went a little further than we have to, but I'll bring it back. So this is what's happening in section 2.1 for the most part, is stuff like this or stuff like that average velocity problem, which is still the same idea. We're stepping closer and closer and closer, which is the same idea as finding the slope at a point. We're stepping closer and closer and closer. I like it. Okay. Then we got into more visual problems, more general ideas about limit. We did a problem, we did a worksheet, this worksheet here. Remember that? If you don't have one, you can have one if you want. I don't know if I gave this to everybody. And that really mostly illustrated the idea that so for which one of those does a limit exist? At A. I love it. And why does it not exist at B? Because the limit from below doesn't agree with the limit from above, right? If you're driving down the road, you don't agree on where this, whatever this thing is, and where it is, right? They filled the hole in. No, they didn't. Where are you? Oh, shit. Right? They don't agree. So there's no limit there. What is f of A, though?
Doesn't exist.
Yeah, undefined. I like it. So it's actually, it's kind of nice. It's not that horrible. It's pretty simple. It's pretty straightforward, thank the gods, right? For a limit to exist somewhere, it's got to agree from below and above. like it. We are going to get into something that a lot of my colleagues skip, and you're all like, oh shit, I should have taken somebody else. Some proofs of stuff. But I don't like to skip it because it comes up over and over again throughout this whole book. It says, remember this? And if you didn't do it, you're like, no, I don't remember this shit. So I try to help. Okay. One thing I didn't specify too much last time, with the idea of limit, trying to find the slope somewhere. I think I did say this, but the problem is trying to find what's called the tangent. So let me put the hold. So this is f of x. This would be the tangent to f of x at x equals a. Notice how there's a certain problem that's going to come up over and over again this semester. Find the equation of the line tangent to this f of x at the point A. So once we learn enough calculus, I'm going to be able to figure out the slope of this. And if I have a slope and a point, I should be able to figure out the equation of the line. Right? And what was, somebody remind me, what equation would you use if you had a point and slope? What would be the equation you would use? So you could use this. To be honest, you could figure out what b is by plugging shit in. Or you could use this one. The only reason I like to try to use this one is it relates directly to something we're going to do later this semester. It completely just directly relates to it. So I love to have this in your brains a bit more, so when it comes up, you're like, oh, it's just this, with calculus shit thrown into place. Like, oh. Okay, so there's a method to my madness sometimes. So this is what they call in 2.1 the tangent problem. The trouble with triples, the trouble with tangents. And we talked a little bit, I do remember we talked a little bit about, like here, what would the tangent line slope be? What's it doing? How's it? So another way to think about, let me see, do I have something I can, yes I do. See if we can do this without involving any deaths of students. Hey, real quick, if I were to twirl this sucker around, and let's say I had something attached to the end of it, and it came unattached, it came flying off. How is it going to fly off? It's going to fly off, so it's making the circular motion, and every point has a tangent to it. Right? So if it suddenly just detaches from the thing, keeping it moving like this, it's going to follow its tangent line. Right? I like that. All right. Raphael? So you're from the Math Study Center? He's going to tell you a little bit about that. We are going to go by there probably tomorrow. But since you're here, you might as well tell him some stuff.
That's a good presentation. Hi guys, my name is Ridal Yako. I'm one of the lead tutors here at the Math Study Center at Grossman College. So basically the Math Study Center is a free tutoring service provided by Grossman College for you guys. So you guys can come into the Math Study Center and ask for help free of charge. So we specialize in mathematics, so basically whenever you need help in a mathematical problem or a concept, you can just stop by and we can provide all the help that you need. We're basically located in the Tech Mall, specifically room 112, and we're open Monday through Thursday, for the summer only, Monday through Thursday, from 8 a.m. to 5 p.m. So Monday through Thursday from 8 a.m. to 5 p.m. And basically you can come in there and ask for help, take a seat. Whenever you need help, you have a small board that you can just put your name on it, and then whenever it's your turn, we'll come up to you and help you. There is no limited number of times of how many you can get, how much help you can get. You can basically stay there technically all day long. There is no appointments or whatsoever. It's just basically a walk-in service, and it's designed for you to get as much help as you need in order to succeed in your class. We have computers over there as well, and so if your homework is online or something like that, you can use these computers. We have tables and tutors assigned per shift available for you that can provide you all the help that you need. And basically, pretty much that's all. It's a great environment. I've been working with Rail for like 5 years by now. It's just a day better than the other. It's something that I really enjoy. And I was a student like you guys too. So it's a great environment. So stop in there whenever you need help, and that's pretty much it. Are there any questions that I can answer before I take off?
I know Mark's in there this summer. Who else? And you, are there some others or no?
Yeah, me, Mark, Colin, Jack, and some others too.
Cool. And all of them can help with 1A.
Math
Because that's
180,
the
yeah.
minimum requirement for being a tutor in there.
Yeah, exactly. I mean, pretty much most of us can help you with any math level that you want. Me specifically, I can help you up to Math 35, which is the last math class that you could take here at Grossman College. So, yeah. All right, guys. Yes,
Where
questions?
is it located?
It's in the Tech Mall, which is Building 70, and specifically room 112.
Yeah, we're going to run by it tomorrow. Yeah.
Do you have books there?
Yes, we can lend you the books, but they have to be only in use. Okay, so when you're only in the West Side Center, we can lend you those books.
And calculators.
And calculators,
Yeah.
yeah.
While you're in the West Side Center, you can check those out.
Exactly.
What is the registration process with the math center?
Oh, there's no registration whatsoever. You just come in,
do
it's
the
a walk-in service.
site ID?
Yeah, but when you come in, you have to, we have the front computer, the computer at the front. You just sign in with your student ID, and before you leave, you sign out, and that's pretty much it.
Do you have to have your ID?
It's just a number. When you have the ID number, you just type it into the computer,
Okay.
and that's it.
Do you guys have like many English speaker tutors?
We all speak English.
I mean like fluent though, because like sometimes I have like a problem like understanding accents.
As far as I know, everybody speaks English fluently over there. I don't think we have anybody with English problems.
Yeah, it's a requirement.
It's a
they're able to
requirement, yeah.
communicate well with the
Because
students.
like some people when they get nervous explaining problems, their accent gets really thick, and I'm just like, what's going on?
Just ask them so that.
Yeah, you should be fine. Okay. Any other questions? Cool. Thank you, Professor.
All right, thank you guys.
Thank you.
Oh, so right here at this point, obviously, if you're on a roller coaster, I've watched a few too many horror movies, but but you get on a roller coaster, and right here you detach from the rails or something. You're gonna start straight. Very soon after that, you're going to be pulled down by gravity, of course, but immediately you're going to be following the tangent line at that point on that curve. Right, so that's kind of a general way you can imagine every function is like a particle following this path. If somehow it becomes detached, it's going to follow its tangent line because it's like the last command it got. You see what I'm saying? It's lost its programming, now it's just going to follow that last thing. Okay, maybe. I think I mixed a few metaphors there, but oh well. The particle roller coaster that's being coded with programming. Okay. Let me see. Anything else I forgot that we did? Oh, all right. And one of the things we did get into was some algebraic ways to really prove what a limit is. That graphical approach. The table approach is not very trustworthy because maybe it's 1, maybe it's 0.999999992 or something. So to really prove it, I want to use algebra if I can. So if I had something like this, we did one like this the other day. I think we did exactly this one. Then one approach, of course, is to use factoring to simplify it. And the whole idea, it's a really beautiful idea. What is it about this problem that causes the indeterminate form is that x minus 2 factor. So if you can kill that problem, you don't have a problem anymore. It's kind of awesome. If I said this, and I know we say this in algebra, and depending on your teacher, they should point out that this is only true if something. If I say this is an incorrect statement. But if I say this, it's perfectly fine. Why?
Because the instruments don't limit part on the bottom.
Why does that make a difference? Is this true, period? No. What should you have to say This is only true as long as x is not 2. What's inherent in the idea of a limit?
That's not 2.
It never gets to this. So it's never 2. So this is a completely fine statement. This needs a little something extra. Right? This is beautiful because the limit says I don't get there. Right? It said blob creature. I don't want to touch that shit. I just close it and say, oh shit, and run away. Right? Then the movie never happens, and it's a cool movie, so I'd rather he touch it and get the movie going. Okay. All right. So that kind of catches it up to where we are. 2, 3 really, at some point, whenever you're talking about some algebraic idea, like the idea of a limit here, there's got to be properties or laws that they have to follow, or things that they're allowed to do. So, sort of like the properties of powers, so forth. So, like the limit laws, I think, yeah, that's exactly what this book calls it. Limit laws. Let me see, blah, blah, blah. Now, thankfully, I'm going to save myself from a lot of writing. So this looks like it's distributed. You should be smarter than that and realize it's not what's happening, but all it's saying is the limit of a sum of functions is a sum of the two limits. And on one level that should make sense. Graphically, if I have a function that looks like it's going somewhere and another function that looks like it's going somewhere, then the sum of them, should look like the sum of these. That's where it's approaching. If I add those two functions together, then it should, where are they approaching? The sum of those two places they were approaching individually. So the same thing happens, just to save some writing. If it was the difference, of course. If it was the product. If it was the quotient. The one thing about the quotient, of course, is that what restriction do I have to put on for the quotient? If it's f divided by g, the limit of g's can't be 0. So for this guy, okay. So they're summed up at the beginning of section 2.3. Those main ones, right? Then we get into, there's one extra little one. This kind of makes sense. What would a constant multiplier do? What transformation would that be? If I had like 2 square root of x, it's going to make the square root of x bigger, right? All the outputs are not twice as big. If all the outputs are twice as big, then the limit, the limit of the function, if I multiply by 2, it should be twice as big as it would have been otherwise. So it looks like the c just comes out. Does that make sense so far? The limit is a very, very basic idea, so it should work really well with a lot of these operations. Okay. Now later they make a good theorem related to some of these next ones. Let me see if this makes sense. Let me call this 1, 2. Why do they still exist? Have any of you ever went running? Oh my God, let me see what's happening. Sorry. So let's do a concrete example of this. And this actually, I want to show you something. Every limit problem we've done so far has had a problem that we had to remove or make a table to investigate. I could take the limit of any damn thing I want to anywhere, and the answer could be whatever. So for example, I could take the limit as x goes to 2 of x minus 7 to the 5th power. So what this is saying is, this is the same thing as the limit as x goes to 2 of x minus 7, all of that to the 5th power. So really all that's saying is, plug a 2 in, right? Why don't I have to be careful here? Why don't I have to be careful and put something in? Because this guy has 0 problems, right? When I plug a 2 in, I don't get an indeterminate form. I get something determinate. It determines the answer, and I'm done. What would the answer be here? Yeah, negative 5 to the 5th. Which is whatever the hell it is. 3,000 negative. Maybe? Okay. 625 times 25, that sounds about right. You guys? Did you do 5? 4? I'm not going to worry. Nobody's double checking. So in general, let me just cut to the chase, because they do several after this. They do the radical and so forth. As long as the function that this is in is what's known as continuous, which we still have to talk about, then this rule works. So for example, square root function. If I have an f of x inside of a square root function, then that's going to be the square root of the limit as x goes to a. See how the limit goes into the function, and I'm telling you a little bit ahead of time. This works if this function that this guy is in is continuous. It can just go into it. Okay, I like it. So section 2.3, most of it is going to be like the limit where you have to do something algebraic to solve it. We did the conjugate stuff, remember that yesterday? What else kind of weird stuff? Well, it was conjugate, and it was factoring, and then it was tables.